To build a marine port, you have to design for an environment that actively wants to tear your structure apart. These walls need to stand up to 50 years of crashing waves, shifting tides, and massive shiploads. This diagram shows how we keep the front retaining wall from collapsing. We use a Deadman anchor tie rod. Its entire job is to transfer the horizontal earth and water pressure away from the front wall and back into a stable, buried anchor block. You might look at a massive steel sheet pile and think it's the most critical point of failure, but when these structures collapse, the wall itself rarely breaks or bends first. The British Standard 6349-2 confirms this. It explicitly states that retaining wall failures are most commonly caused by the failure of the anchorage system holding it back. If the tie rod snaps, the wall comes down. Protecting and optimizing that buried rod is the single most critical engineering task for making sure a port survives its design life. When faced with a load that critical, the standard engineering instinct is to max out the specs. You specify the highest yield strength steel available to save weight, and you cover it in complex coatings to stop the salt water from rusting it. On paper, this solves two problems at once. Lighter, thinner bars cost less to ship, and a thick marine coating forms a supposedly impenetrable barrier against the ocean. But pushing marine steel to extreme strengths introduces an invisible threat. Under high tension and saltwater environments, ultra-high-strength steel becomes highly susceptible to hydrogen embrittlement. It can crack and shatter completely without warning. Because these failure modes are completely invisible until the moment of collapse, global design codes like EN 1993-5 actively prohibit this approach for Deadman anchors. To build a reliable marine wall, we have to unlearn the instinct that stronger is always better. Instead, we have to navigate two specific, highly counterintuitive trade-offs regarding the steel grade we choose and how we protect it. The first decision is specifying the correct steel grade for a passive marine Deadman anchor. We have to balance raw tension capacity against stress corrosion cracking, or SCC. This is a specific type of degradation that specifically attacks high-yield metals exposed to seawater. This chart compares European and US steel grades and maps their risk levels for stress corrosion cracking. If you specify an extreme high-strength steel with a yield over 800 megapascals, you enter the high-risk zone for severe SCC, which leads to sudden, unwarned failure. Because the risk is so high, the EN 1993-5 code completely bans any grade above 800 megapascals for passive Deadman anchors. Even stepping down slightly to a 700 megapascal grade is restricted. That grade is strictly reserved for active, pre-stressed ground anchors and is totally unsuitable for passive marine walls. Look at the top rows. Grades 355 and 460 sit in the no or low risk category. These are hot-rolled, high-ductility steels that provide the optimal balance of strength and elongation to survive a 50-year lifespan. You are trading a slightly thinner shaft for a lower-yield, ductile grade. This ensures strict code compliance and guarantees the steel will stretch and give visual warning of an overload long before it snaps. Once you have a compliant, ductile steel, the second major decision is protecting it from aggressive saltwater over its 50-year design life. The first option is applying a hard coating, like galvanizing or specialized marine paint. This process flow diagram shows the 7 distinct steps required for a coated system. These coatings demand a complex sequence, where chipping during transport is almost guaranteed. That forces your site team to spend hours manually touching up damaged spots in the mud and water. The second option is petrolatum wrapping. Wrapping demands highly skilled site labor and causes massive execution delays. Even worse, the complex anchor joints are notoriously difficult to wrap correctly, leaving them highly vulnerable to poor application. The third option bypasses these site issues entirely: sacrificial steel. This table from the EN 1993-5 code shows the recommended steel thickness loss due to corrosion based on specific water types and design life. Instead of fighting the rust, you calculate exactly how much steel will corrode over 50 to 100 years, and you intentionally add those precise millimeters of thickness to the bar at the factory. Sacrificial steel increases the upfront physical weight of the delivery by roughly 9%, but it objectively wins because it completely eliminates all site labor, maintenance bottlenecks, and installation delays. The contractor just drops it in the trench. Adding uniform thickness across an entire 20-meter tie rod is an inefficient way to utilize sacrificial steel. It makes the system excessively heavy and expensive to deliver. Standard threaded bars illustrate why. When threads are cut directly into a shaft, material is removed, making the critical connection joint the narrowest and weakest point of the anchor. Without extra thickness at the connection, an overload causes the anchor to fail suddenly at the threads, providing zero elongation or visual warning of the structural stress. Upset forging changes that dynamic. By expanding the rod ends before threading, you ensure the thread's cross-sectional area remains larger and stronger than the main shaft, even after the threads are cut. This focused geometry is what makes sacrificial steel a practical engineering choice. It allows you to place thick protection at the vulnerable joints while keeping the main shaft optimized, cutting total weight by 30% while ensuring a fail-safe stretching sequence. The definitive choice for a marine sheet pile design is clear. Specify a ductile grade 355 or 460 steel, protected by upset forged sacrificial steel. For the EPC contractor, eliminating specialized site treatments protects the schedule and secures project margins. For the design consultant, this configuration ensures ironclad compliance with IS 9527 and EN 19935, completely mitigating the liability of sudden brittle failures. Both the builder and the designer achieve their primary goals by accepting a counterintuitive trade-off, taking on a slightly heavier initial material delivery in exchange for flawless execution. Ultimately, these decisions roll up to the stakeholder who lives with the infrastructure for decades, the port owner and developer. Owners need an anchorage system capable of surviving immense surface loads and natural ground settlement. It has to do this for 50 years without requiring expensive underwater inspections or causing catastrophic operational downtime. Making these specific upfront engineering trade-offs directly guarantees the port's long-term operational stability and protects the massive return on investment. Engineering a predictable, fail-safe system provides a level of resilience that raw material strength alone cannot match.